Okay, so in this video, we're going to be describing some key characteristics of a function, of a polynomial function. So first key characteristic here is to determine if the graph is even or odd. And you can tell that using the idea of end behavior. If you call it end behavior, an even function will have both sides either pointing up or both sides either pointing down. Both sides point in the same direction, basically. And if you recall the discussion about end behavior, for odd functions, one side will point up while the other points down, or vice versa. Left points up and right points down. So based on this, since the left side is down and right side is up, I can say that this is an odd polynomial function. The next characteristic we're going to look at is extrema. And now this one doesn't have any absolute extrema, which are the highest or lowest points. However, it does have some extrema, one right there and one right there. Those would be relative extrema because they're not the highest or lowest points, but they are highs and lows. So we will have to approximate them just because they are not exact values. So this order pair first. For this extrema is approximately negative 2.5, not exactly that, and about positive 0.9 on the y-axis, so I'll put 0.9. And that is a high point, so it would be a maximum, and because it's not the highest point, we're going to call it a relative or local maximum, which means it's a high point in that general area. The other one down here is a low point. It's a little bit off of the y-axis. It's not quite on the y-axis. So this would be a minimum, and it's approximately, it's not quite the y-axis, so I'm just going to call it negative 0.1. It's really close to the y-axis. It's like right there. So I'm just going to approximate it as negative 0.1. And the actual y value there, if you look at it, it's not quite at 6. It's a little bit below the negative 6 there. So I think I will approximate just a little off of the negative 6. So negative 6.1 maybe. Sounds like a good number to me. Just to kind of emphasize that it's not exactly at negative 6. If someone else were doing this, they may approximate the numbers slightly differently than what I did, but should be the same general vicinity. And as far as the description for this is a low point, so it would be a minimum. But because the graph goes down farther, it's not the absolute lowest point, so we would just call it a relative or local minimum. So the next characteristic we'll look at is end behavior, and we've done this before. So I'm just going to quickly describe it with the words. Left side is pointing downwards. Left side goes down and off the graph. And then the right side here is going up and off the graph. So right side goes up. And just using the words isn't really great for Algebra 2, so let's go ahead and push further and do the algebraic descriptions. Left is an x descriptor, and the type of x values on the left are negative, so x approaches negative infinity. And down is a y descriptor, so y will approach. Well, negative y values are down, so negative infinity. Right is an x descriptor, so x approaches. Well, positive x values are on the right. And up and down are y descriptors, so y approaches. And then for up, positive y values are up, so positive infinity. So here are the two end behaviors. The next characteristic we'll look at is describe where the function is increasing, decreasing. So at first it goes up until we get to this point here, which if I put my dotted line, like we've done in the past, I should probably erase my earlier dotted line so we don't get it confused. So that's where it stops increasing, and then it stops decreasing about right here. It's just off of the y-axis, the same point as our extremas were. So those extremas split the graph into 3 segments, those highs and lows. The first segment is here. The second segment I'm going to leave in white, and then the third segment is over here. So the 3 intervals go from negative infinity until my first extrema, which we approximated earlier to be about negative 2.5-ish. The second interval is from negative 2.5 to about negative 0.1, which is what I approximated the x value to be earlier, just keeping it consistent. And then the last one will be negative 0.1 until positive infinity. So those are my three intervals. And on the first interval, since we're doing increasing, decreasing, that's from left to right. The first interval is increasing. Second one is going down, so decreasing. And third one from left to right is increasing again. So the two increasing intervals are from negative infinity to negative 2.5 and negative 0.1 to infinity, while the decreasing interval is negative 2.5 to approximately negative 0.1. And we have one more characteristic we're going to look at, and that is intercepts. So there's two types of intercepts. There's the x-intercepts, and then there's the y-intercepts. You can either describe them with order pairs, or you can describe them as a list. I prefer usually to use the list. So for my x-intercepts, that's where it crosses the x-axis, and there's 3 spots. Negative 3 is one, negative 2 is another, and then 1 is the third. Depending on what the degree of the polynomial is, depends on how many x-intercepts it could have. So it can have more or less than the amount of x-intercepts that we have for this particular problem. Y-intercepts, though, a polynomial will only ever have one y-intercept. You can see that y-intercept is down here. I think it might be exactly at negative 6. It looks to be exactly on there, so I'm just going to approximate it at negative 6. I'm not 100% sure. But it looks dead on, and same thing with the x-intercepts. That's why I didn't really take too much time looking at them, as they appear to be exactly on. In some cases, you might have to approximate them, depending on the situation that you're looking at. But there we go. There's some key characteristics of this polynomial function. Okay, in this example, we're going to find the average rate of change of this function on the interval of 0 to 2. Now, average rate of change, you may recall from earlier in the year or from an earlier course, is just another word for slope. So you could use any variation of the slope formula to calculate the average rate of change. So you could use rise over run, but that's more suited for a graph. You could use y2 minus y1 over x2 minus x1. Or because this is Algebra 2 and we're focused on preparing for certain courses, we're going to use f of b minus f of a, where those are representing the y values, over b minus a. No matter what, in order to do this, though, we do need the y values. So I'm just going to go through and label. There's my a and b, and we need to figure out what f of a is. We need f of 0 here. And f of 0 just means to plug in 0 for x. So I'm going to go ahead and do that. If I replace x with 0, we'll have negative 0.5 times 0 to the 4th plus 3 times 0 squared plus 2. And if you either do this by hand or type it into the calculator, you should get the answer 2. So the y value here is 2. Then we will also need f of 2 in order to actually do this. We'll need the y value with 2. So if I do the same thing, negative 0.5 times 2 to the 4th plus 3 times 2 to the 2nd plus 2. And whether I do this by hand or I type it into a calculator that can do order of operations, I should get 6. Now that we have our two y values, we can go ahead and apply the slope formula. So we have f of b, and our b would be the second x value in the interval, minus f of a over 2 minus 0. F of 2 we just went through and calculated. F of 2 is 2. No, sorry, looked at the wrong one. F of 2 is 6. Minus f of 0 is 2. Just looking at what we found earlier. This is over 2 minus 0. Now we just have to do some simple math. 6 minus 2 is 4, and 2 minus 0 is 2. 4 divided by 2 is 2. So the average rate of change is 2, which means this graph approximately goes up 2 over 1, up 2 over 1, between the x values of 0 and 2. Okay, so in this example, we're going to be looking at the function f of x equals x to the fourth minus x squared plus x, and we're going to do each of the following. So we're going to identify the end behavior. We're going to find the y value for each of these points, each of these x values. We're going to sketch the graph based on the information we found, and then we're just going to identify or label some key points like extremas, and x-intercepts or y-intercepts, whatever we can actually label with the information that we actually have here. So to start with, we need our end behavior, and we can do that just using the degree and leading coefficient. So for the end behavior, our degree is 4. And our leading coefficient would be 1, because there's no coefficient there, so it's implied to be 1. So that means it's even degree with a positive leading coefficient, which means I know the end behavior is going to look something like this, where both sides are pointing up. We went over that in an earlier lesson, and this is just a property of polynomials that we're using here. So I know the left side goes up, and so does the right side. And if we want to turn it into mathematical notation, x will approach negative infinity, while y approaches positive infinity. And the right side, x approaches positive infinity, while y approaches positive infinity as well. So there we have it for end behavior. Part A, done. Part B, we need to identify the y values for each of these x values. That's done simply by plugging each of those values in. So for the first one, we would just plug in the negative 1.325. So we'd do negative 1.325 to the power of 4 minus negative 1.325 squared plus negative 1.325. And we'd either do this by hand or type it into the calculator. If I type it into calculator, negative 1.325, we get this lovely small number of 0.002 if I round to 3 decimal places there. And as an ordered pair, that would give us negative 1.325, comma, 0.002. If we do the same thing for negative 0.9, we'd have negative 0.9 to the fourth minus negative 0.9 squared plus negative 0.9. If I type that into the calculator, let's see what we get, negative 0.9, we would have about negative 1.054 if I round to 3 decimal places. Sorry, wrong one. Negative 0.9, comma, there we go. And then our last point is 0. 0 is nice. I love zeros. So we'll have 0 to the fourth minus 0 squared plus 0. Don't even need the calculator for this one. Everything comes out 0. So our last point is 0, comma 0. So those are the 3 points that we have. And that last point is actually the y-intercept, because the y-intercept occurs when x is 0. Now let's go ahead and sketch this graph based on the information we pulled here. Since these are probably approximate numbers, intending to hit certain points, they might actually be x-intercepts and stuff. I'm going to guess this one's intended to be an x-intercept, that first one there. So I'm just going to go ahead and plot some points. -1, -2. Looks like that's all the farther I have to go out. Oh, why did I put negative? 1, 2, and 3. 1, 2, 3, and -1, -2, and -3. 1, 2, 3. Okay, so first point, let's go ahead and get it. First point here is -1.325. So somewhere in between here. And then we have a positive 0.2, so it's just off the x-axis. I'm going to assume it was probably intended to be on the x-axis and that the actual x-intercept is irrational, which means a decimal that goes on and on forever, so it throws things off a little bit. But if we look at the second point there, we have -0.9 and -1.054. So -0.9 would be about right there. And -1.504 would just be past the -1 mark, so about right there. And then, let's see, what else do we have? We have 0, 0, so we now have to go through 0, 0. So I know that my graph is going up on the left and up on the right. So we know it has to go maybe something like this. Probably not the best graph. Something like that. It might have a little bit more shape, but based on the context that we have, the information that we have, that's the best we can do. And then just to label some of the key points, which is what D is saying, this is probably an extrema or a minimum, which is actually that point there. And we have an x-intercept and a y-intercept with the point 0, 0. And most likely this point here, because it's rounded, is probably an x-intercept, but since it's not actually there, I'm not going to label it as such. But it was intended to be an x-intercept using approximate values. We haven't actually gotten to the point of finding solutions or roots from polynomial functions yet algebraically. So that's as close as we can get with that. And if you want to check out what this graph actually looks like, you can pull up a graph on Desmos and just compare, which I might actually do if I have Desmos still open. I do. So let's go ahead and type that in and just see how close we kind of have stuff. X to the fourth, minus x squared, and then plus x. So that's what we have. So the curve, we don't have quite the curvature going on, but we do have the key point. We have the extrema there, which again is an approximate value. It's not quite -0.9. It was rounded, and -1.325. I know that's the exact value, but Desmos will cut it off and round it at the third decimal place. So I imagine since we didn't get 0 when we plugged it in, it's actually kind of rounded. And then, of course, 0 is 0, which we had exactly. So those are some of the crucial points in this function.